Hello everybody, this is Carmichael the Cat, and welcome to your 10th Lua 5.2 tutorial. In this video, we're going to be going over some more advanced tables, so this video is going to have a lot more new stuff, unlike last video, which was more just concept driven. So the first thing we're going to go over in this video is the colon syntax for Lua's class/tables. We'll call them pseudo classes. And the colon syntax is going to allow us to get rid of those redundant parameters that we had in our member functions of our player class in the last video. So we'll create a new class, we'll call it vector2, and this will be equivalent to a two-dimensional vector in geometry, so it'll pretty much be just representing an x and y position on a coordinate grid, and it can do a few more things that we'll get to later in the video. So it's, the vector2 is going to have two member variables, x, which is set to 0, and y, which is also set to 0. And then it will have another variable. It's not technically a member variable, and we'll set it to empty table. So call it empty and set it to empty table. Don't worry about this for now. We'll get to it later in the video. And then we'll create our constructor. It's going to be very similar to the constructor in the last video, because these classes are pretty similar, at least for now. So we'll create a new local variable. We'll call it vec. And instead of using the generic for loop in this video, we're just gonna, since this class doesn't have quite as many members as the player class, we're just gonna list off each member. So we'll say vec.x equals vector2.x, vec.y equals vector2.y, y, and vec.mt equals vector2.mt. So this, I know this looks a bit unclean and overexpanded, but we will completely be getting rid of it later in the video when we get to metatables. So we'll get to that later. So now we're just going to return. I'm bad at typing today. Return vec, as you can see. So we return our vector, and this is our constructor. So now let's go down here, and we'll create our first instance of this vector2. So v1 equals vector2.new. So far, nothing new from the last video. And we'll just set v1.x to 10 and v1.y to 20. There we go. So now let's create our first member function in this class, and this is going to be very similar to the move function that the player had in the last video. So we'll call this one translate, and we'll set it to function, and it's going to have three parameters just like the move function that the player had. First one's going to be called self, and notice how ZeroBrain highlights it in kind of purplish color. That's because self is a special parameter, and we'll get to y in a minute. And then change in x and change in y, or delta x and delta y. Then we'll end the function, and the body of this function is going to be very similar to the move as well. So self.x is self.x plus dx. I really wish Lua had a plus equals operator. And self.y equals self.y plus dy. So now we have our first member function. So we need to add to our list here where is it? I'm horrible at typing today, I'm sorry. Translate equals vector2.translate. So now we can call this function, and if you remember from the last video, the way we would have called it is v1.translate. It's not auto-completing for me. Translate, and we would pass v1 as the first parameter, and we'll just say 10 and 10, so 10 on each axis, as the second and third parameters for change in x and y. And then we could print the values of v1, so print v1.x and v1.y. So now if we run this, oops, we get an error. I forgot to put a comma after this function. That's a very easy error to make, but not too hard to fix. And now we get another error. 1 second, I'll fix this. Alright, so the problem was that I didn't declare vec as a table, so now it should work. And it does. We get 20 and 30. So v1's value started at 10 for the x value and 20 for the y value. And then we translated it by 10 on each axis, and it became 20 and 30. So the function works, but we're still stuck with this kind of redundant syntax of saying v1.translate with the parameters v1, 10, and 10. But we can get rid of this now that we're using this parameter called self. So we just get rid of this, and now we change the dot to a colon. So now it says v1, and we can still just say dot, v1.translate by 10 and 10. So if we run this, we get the same thing, 20 and 30. And this colon is really just a convenience thing that Lua adds, and basically what it does is it just kind of replaces this with a dot. Behind the scenes, this is replaced with a dot, and v1 is added back here. So whatever value is here is put back here, and it will take the place of the self parameter in this function. So this is obviously a more clean way to call a function, and it doesn't have that redundant v1 parameter. So you should always use this when you have a member function that modifies the class itself. So remember to have that extra self parameter, and I believe you can actually name it whatever you want. I guess we could call this x, and actually that wouldn't work. Let's call it p. I'm not sure if this will work. I'm testing this out for myself. So p.x, p.y. It's kind of a waste of time. It doesn't really matter, but it's interesting to see. And if we run it, we get the same value. So you don't actually have to call the first parameter self, but that's the general convention that most people use. So I would recommend calling the parameter self, but you don't have to. So now that we understand the colon syntax, let's move on to metatables. So if you're familiar with operator overloading in C++ or any other language that supports it, this should be pretty similar to you. What metatables allow you to do is they allow you to define behaviors like, say, addition, so adding two classes together, or subtraction, subtracting two classes, or even things like using the less than or equal to or greater than or equal to operators, or even assigning values within a table. So it allows you to define what happens when you try to do that to your table. So this table we created right here will be the metatable for our vector2 class, and we have to set this metatable to each instance of our vector2 that we make. So to do that, we say set metatable, and it's a predefined function in Lua, and the first parameter will be the table that we want to have the metatable set to. So in this case, our local vec table. And the second parameter is the metatable, so it is vector2.mt. So now any what are called meta methods that are defined within this mt table will be applied to all new instances of the vector2, and then whenever we have instances of the vector2, we can use any of the meta methods between those instances. So say if we added an add meta method, then we could add two vector2s together. If we had a sub one, we could subtract them. If we had a less than operator one, then we could compare them with the less than operator, and so on. So let's create a meta method. We'll say vector2.mt and the function has to be called __ add for the addition meta method. So remember the two underscores. And we'll set it equal to function, and it will just take two values, v1 and v2, which stand for vector1 and vector2. And we will end. And now, in this function, we're just going to create a new vector. We'll call it vec equals vector2.new. So we'll create a new vector2. And then we're just going to add the x member, v1's x member to v2's x member, and v1's y member to v2's y member, and set those values to vec's x and y members. And that's how addition for vector 2's is defined in math. So we'll say vec.x equals v1.x plus v2.x, and vec.y equals v1.y. Oh, minus equals, that doesn't exist. v1.y plus v2.y. And then we'll return, I'm very bad at spelling return today, we'll return vec. So now, since we've created this add meta method within our vector2.mt table, and we've set the vector2.mt's table as the meta table for each new instance of the vector2 class, we can now add just add right now, we can now add any two instances of the vector2 class together. So let's create a new one. We'll say vector2 or v2 equals vector2.new. There we go. And we'll say v2.x is 30 and v2.y is 40. So now we'll create a v3 and we'll say v3 equals v1 plus v2. And then we don't really need the extra line here. Then we'll print v3's values. So v3.x and v3.y. So now we've added two vector 2's together, which by default, since they're tables, isn't possible because there's no predefined behavior for adding two tables together. But with this meta method that we've added to our meta table and then set to each instance of our vector2 class, adding two vectors becomes possible. So if we run this, we get 40 and 60. So the first value that's output is v3.x, which is set to v1.x plus v2.x, so 10 plus 30, that's 40. And then we get 60, which comes from v3.y, and v3.y is v1.y plus v2.y, so 20 plus 40, and that's 60. So the vectors are properly added together, and we did it with the addition operator. So we can do a very similar thing for subtraction. So let's add a new function. So we'll say vector2, not vector1, vector2 dot mt dot underscore underscore, and the meta method for subtraction, or the subtraction operator, is sub. So you say mt dot underscore underscore sub. And then other than that, it's pretty much the same thing. We have a function v1 and v2 as parameters. We end it, and we can really just copy the body of the underscore underscore add function into this. And then we can just change the operators here to subtraction instead of addition. So now we are subtracting the separate members of the vectors and returning the new vector. And this is part of the same MT meta table, so we're already setting this meta method to each instance of the vector2. So now, if we were to change this operator to v1 minus v2, and we run it, we get negative 20 and negative 20. And the first negative 20 comes from v3.x, which comes from v1.x, which is 10, minus v2.x, which is 30. So 10 minus 30, that's negative 20. And then we get another negative 20 from v3.y, which comes from 20 minus 40, so that is also negative 20. So as you can see, the subtraction worked properly. And you can also add meta methods for all of the other mathematical operators, or mathematic operators. So there is underscore underscore mul. I used the wrong comment. There's underscore underscore mul. This is for multiplication. I'm not going to show examples of functions for each of these because they're all exactly the same as these two, except you'd replace this operator with the respective operator for each meta method. So there's mul. So for a vector 2, yeah, I guess you could do the dot product of to vectors, and that would return a number or a scalar. And then there's underscore underscore div for division, and you really can't divide vectors, so that really doesn't apply to this class. Then I believe for modulus it's underscore underscore mod, and again that really doesn't apply for vectors. I guess you could get the remainder of each separate member, the x and y members, like we do with the addition and subtraction. But there is really no mathematically defined modulus operation for vectors. So these two don't really apply, but the underscore underscore div and underscore underscore mod meta methods are, you can create them for your classes if you want to. And this is how you would do it. You just replace the underscore underscore sub or add with mul, div, or mod, and create the respective function for that. So those are the math operators, and now let's move on to the comparison operators. So the relational operators, which are the less than or equal to, greater than or equal to, and not equals to operators, they work slightly differently than the math operators, not in the way that we declare them and apply them to classes, but in the way that we write the functions. So if you remember from the operators and if statements tutorial, I believe it was the logic statements tutorial, that's what it was called, the relational operators all take two values, one on the left and one on the right. They're the values that are compared, and the operators return either true or false, depending on whether the condition that they present is satisfied. So really the only two that work with vectors are equal to and not equal to, and since all the relational operators work pretty much the same way, we're only going to do one. And then I'll write out the names of the meta methods for the rest of them, just like I did here for the math operators. So a vector2 dot mt dot underscore underscore eq is the one we're going to do. It's the equals to operator. Equals a function. And as parameters, again, we give it v1 and v2. And then end. And this function is just going to be one line. It's going to say return v1.x equals v2.x and v1.y is equal to v2.y. So we're pretty much just checking whether the x and the y variables, or x and y members of each vector, are exactly the same. And we're returning true if they are and false if they're not. So now we could print v1 equals v2, and this should print false because, as you can see, their x and y members aren't equal. So under our -20 and -20, we get false. So it works properly, and we can now compare vector 2's with the equal to operator. And the rest of the relational meta methods are underscore underscore lt for less than, underscore underscore le for less than or equal to, underscore underscore gt for greater than, underscore underscore ge for greater than or equal to, and there is no meta method for not equals to. You would just say not and then the equal to operator. So you can kind of imitate the not equals to operator without it. So I'm not going to write any of these functions because they would work the exact same way as this function. You just return, I mean, none of these functions in math are defined for vectors, but I guess if you wanted to, for vectors, you could say, for less than, you could say v1.x is less than v2.x, and v1.y is less than v2.y, and for less than or equal to, you could replace the less than with a less than or equal to operator, and so on. So they work the exact same way. They just take in two values and return true or false, depending on whether or not they satisfy the condition given by the operator. So that's how the relational meta methods work. So the next two meta methods are kind of miscellaneous, so we have to create both for vector2 to really show them. The first one is the underscore underscore toString method, And this defines the function toString. We've probably gone over it before, and if we haven't, it just converts pretty much any value into a string. So underscore underscore toString, and it equals function, and this time it only gets one value, so we'll just call it vec, and then we will end the function down here. And this value should return a string since the function is called toString. So we'll just represent the vector2 as a coordinate pair when we call toString. So we'll return open parentheses concatenated with vec.x, and then a comma and a space, and then vec.y, and then closing parentheses. So now, instead of having to do this, we can shorten it and say print vec3, and the print function automatically calls toString on each of its parameters. So this vec3 is having toString and kind of implicitly called on it. So if we run this, we get nil. And that's because we put the wrong variable name into print. I feel silly now. And so now if we run it, we get we get the output values a bit more properly in coordinate pair form. So we get the open parentheses from right here, and then the two values separated by a comma, and then closing parentheses, just like we defined right here. And the next method, it's not really a method actually, it's kind of just a value, so it's called a meta field technically. So we say vector2.mt dot underscore underscore metatable. So what this, we'll call it a meta field, does is it defines what happens when you try to set and get the metatable of this class. So in this case our vector2 class. So you can use this if you want to protect, so say you're creating a library, like a graphics library for a game, and you have this vector2 class to represent a position or an actual vector, and you don't want the people using the library to be able to change or access the metatable of the vector2 class. In that case, you can define this underscore underscore metatable meta field, and then when getMetatable is called, which is another predefined function, which will, in the case of our vector2 table, it will return vector2.mt. So it will return the metatable of whatever table you pass as a parameter to get metatable. So it will return this string instead of that table if you call getMetatable, and it will create an error if they try to use setMetatable on a table with this metafield defined. So we'll just say private. And now if we go down here and print get metatable, just do v3. Then down here we get private. And if we try to set metatable v3, we'll just say nil. And by the way, this is how you delete a metatable from something if this isn't defined. You just set it to a nil value. Then we get an error, the location of the file at line 68, and this is line 68 right here, cannot change a protected metatable. So once you define this meta field, you cannot change the metatable of that class. So that's what the underscore underscore metatable metafield is used for. So the last two metafields / meta methods we're going to be going over in this video are index and new index. So we'll start with index. So vector2.mt underscore underscore index equals, and it can either be a table or a function. So we'll set it to vector2, and this may seem strange, but I will explain why we do this now. So the underscore underscore index metafield is what allows us to delete this kind of unclean and repetitive code. So what the underscore underscore index metafield does is it defines what happens when you try to access a value in the table that doesn't yet exist. So Right now, this would never be invoked because when doing something like this, where we set the new value where we set the new key to some new value, this invokes the new index meta method that we'll go over in a second. But if we were to say call v1.translate, and we'll just say by 10 and 10. When we call this, we are accessing this translate member without changing it. So this would invoke the __ index meta field / method. And then what we're saying is that if it doesn't exist within the table v1, which it doesn't since we deleted the all the sets to the vector2 values in the constructor, so translate doesn't yet exist when we're calling this line, then it will look within the vector2 table. So we see that it has the vector2 table has translate right here, so it will set v1.translate to vector2.translate. So now the translate function will exist. So that's how you use the __ index meta field. It allows you to kind of shorten the constructor right here, so that we don't have to have all that repetitive code in it. And you can also make the __ index a meta method by using a function instead of a table. So say if you wanted, you could only allow certain values to work the way that they do right here. So say for translate, it would just set it to vector2.translate because that's what we want. But if the user tried to just call some random function that didn't exist from using the vector1, so like vector1.move, that's a function that we never define in the vector2 prototype, then you could do something within the function so that that would raise an error instead of just creating some random value. So now moving on to the vector2, or not the vector2, the new index meta method. So vector2.mt.__ new index. And what we're going to do for this is we're going to change this vector2 class into a read-only table. So we're allowed to create it, and then none of the values within it can ever be changed. So that kind of removes most of the purpose of it, but this is just for example. So the new index meta field takes 3 parameters, t, k, and v. T is the table it's being accessed, k is the position at which it's being accessed, and v is the value of the table at the position of that key. So end. And in this example, we're not going to use any of these parameters. All we're going to do is we're going to raise an error. This function just raises an error and stops the code. So cannot, that's not how you spell cannot change values of vector2 instance. So now if we run the code, we get cannot change values of vector2 instance because we're trying to change a value right here. So the new index meta method defines what happens when you try to set a value to a position in a table that doesn't yet exist. So since we deleted all the assignments to the vector2 members in the constructor, the x and y members don't exist in v1 yet. So when we try to set them to 10 and 20, it invokes a new index meta field, and that raises the error in this case. So that's all the meta fields and meta methods that we're going to go over in this video. There are a few more, but they're not of much use to us until we get to some later tutorials, so we'll come back to them later. So again, that's all for this video. And in the next video, we're going to have a pull tutorial on the generic for loop that I kind of touched on in the last video. So I'll see you then.